In Chapter 8, I want to look at a number of interesting properties of the Fibonacci sequence, a sequence that you've no doubt encountered at some point. So we'll introduce the Fibonacci sequence, and I want to derive a formula for the nth term in the Fibonacci sequence, or the nth Fibonacci number. And then we'll look more generally at linear recurrences and take a look at the associated quadratic equation, where you have to distinguish the cases of distinct roots and the cases of a multiple root. Okay, so what's the Fibonacci sequence? Well, you just start with the numbers 1 and 1, and then you just keep adding the two numbers to get the next term in the sequence. So 1 plus 2 is 3, 2 plus 3 is 5, and so on. So we get this infinite sequence of Fibonacci numbers. Now I'm going to throw in n equals 0, so we'll call this the 0th Fibonacci number, right there, and then f1 will start with 1. And it's governed by the recurrence relationship that the nth term is the sum of the previous two terms. Fibonacci lived in the 12th century. He was the first one to put together all of the important properties of the Fibonacci sequence, although it does appear earlier in mathematics. Now, this sequence of Fibonacci numbers is not the only one that satisfies this recurrence right here. Indeed, we could have started with any two numbers. So in this example, I'm starting with 2 and 5. And if I add 2 plus 5, I get 7. 5 plus 7 is 12. 7 plus 12 is 19. And I generate another sequence of this type. So let's try to find all sequences that would satisfy this linear recurrence. So characterize all sequences un that satisfy un is the sum of the previous two terms. So first, we're going to see if there's any geometric sequence that would satisfy the recurrence. So let's let un be lambda to the n power, where lambda is just some fixed complex number. Then what would we need? Well, then plugging that into the left side, we get lambda to the n is lambda to the n minus 1 plus lambda to the n minus 2. Divide out lambda to the n minus 2, so we're going to assume lambda is not 0. When lambda is 0, you get a trivial solution to this sequence. So we want some non-trivial sequence values of lambda here. So we get lambda squared then is lambda plus 1. Turn this into a quadratic equation. And then by the quadratic formula, we have two values of phi that work. So 1 plus the square root of 5 over 2 and 1 minus the square root of 5 over 2. Those are the two solutions to this quadratic equation right here. The first one you've probably encountered. This is called the golden ratio, 1.61828. And then phi prime is just its conjugate value, which is negative 0.61828. So the sum of these two numbers adds up to 1, which of course is governed by the fact that you have a 1 right here in front of the lambda term. So we have two geometric sequences that satisfy the recurrence. The sequence of powers of the golden ratio and the sequence of powers of its conjugate phi prime. Therefore, by linearity, any sequence of this type, Wn, where you fix a constant c1 and a constant c2, so c1 times phi to the n plus c2 times phi prime to the n, will also satisfy the linear recurrence. So we get this big family of sequences that satisfy the linear recurrence. And we claim that this characterizes all sequences satisfying this recurrence. So conversely, we claim that any sequence satisfying 2 is a linear combination of this type. Okay, so to see this, how do we do? We first observe that any sequence satisfying 2 is uniquely determined by its first two values. Okay, now why is that? Well, once you know U0 and U1, it follows that U2 is that sum. So U2 is determined. And then it follows that U3 is U2 plus U1. And since U2 is already determined, U3 is determined. And so by induction, all values UN are uniquely determined. So, all we need to do to prove the converse is to show that there is some linear combination that would agree with the first two terms of a sequence satisfying 2. Thus, it suffices to find constants C1 and C2 such that we have this agreement in the first couple terms here, that W0 is U0, W1 is U1, where Wn is this linear combination. So that would say C1 plus C2 is U0, C1 phi plus C2 phi prime is U1, and since phi prime minus phi is a non-zero quantity, this should be minus root 5 right here, this system has a unique solution. In fact, Kramer's rule will give it to us. So C1, we take the determinant where I replace the U0, U1 in the coefficient part. And then the determinant of the coefficient matrix is phi prime minus phi. So you get U0 phi prime minus U1. And then phi prime minus phi is minus square root of 5 here. And C2, we replace the second column, so you have 1 phi, and then U0, U1 over minus root 5. So that's U1 minus U0 phi over minus root 5. So it suffices to prove that for any two given values, U0 and U1, there exist constants C1 and C2 such that with the Wn sequence being this linear combination, the first term of the W sequence agrees with U0 and the next term in the W sequence agrees with U1. Well, what does that mean? W0 is just C1 plus C2, and W1 is C1 phi plus C2 phi prime. So we get a system of two equations and two unknowns, two variables C1 and C2, and we're trying to solve for C1 and C2. Well, that's a linear system, and the determinant, if we look at the coefficient matrix, is just phi prime minus phi, which is a non-zero number. So we have a non-singular linear system which will have a unique solution. And in fact, by Kramer's rule, we can solve for C1 and C2 explicitly. So you just put U0, U1, 1 phi prime over the coefficient determinant, like that. And so this is U0 phi prime minus U1 over phi prime minus phi, which is just square root of 5. And likewise, C2 would be the determinant where you put the second column as U0, U1, like that, over the same denominator. And we get U1 minus phi, U0, over square root of 5. Okay, so that proves the claim that every recurrent sequence is a linear combination of this type. Let's apply that to the Fibonacci sequence. So in the Fibonacci sequence, U0 is 0, U1 is 1, and then from the formula we just looked at, C1 is 1 over root 5, C2 is negative 1 over root 5, and thus we get an explicit formula for the nth Fibonacci number. So f sub n is 1 over the square root of 5 times phi to the n minus phi prime to the n, which is really kind of a strange looking formula because these are whole numbers. So it turns out for any natural number n, this expression, which looks very irrational on the right-hand side, is in fact a whole number. In fact, there's a nice way to look at it. How big is this term right here? So this second piece, this is about 0.618 with a negative sign, being raised to the nth power. That's a quantity that's converging to 0 very rapidly with an alternating plus minus sign. Therefore, the size of the nth Fibonacci number is really just this piece right here. And you see, therefore, that Fn, the nth Fibonacci number, is in fact the nearest integer to this value right here. Because this quantity, the second quantity, is going to get much less than 1/2 in size. And that's a nice way to think about the nth Fibonacci number. It's just the nearest integer to this value. And this is just a geometric sequence we're looking at right here. This is a geometric sequence. So the Fibonacci sequence is essentially a geometric sequence. You just get geometric growth. Let's take a look at the calculation using this formula, say with n being 100. So I'll come over to Wolfram alpha, and I put in the golden ratio here, 1 plus root 5 over 2. Raise that to the 100th power and divide by the square root of 5. So I'm just going to ignore the other part in the formula. And when I calculate this, what do we get? All right, let's look what we get with this calculation. Here's the decimal quantity right there. And notice all these zeros here, and it's times 10 to the 20th. So really the decimal point, you have this integer right here, 0.000000000. So this is that little error term. That's the phi prime raised to the n term, this really tiny thing. And the nearest integer is just that first part of the expression. So that is the 100th Fibonacci number. Just take those first 20 digits right here. Now everything we did for the Fibonacci sequence just then generalizes to any second order linear recurrence. So let's take a sequence un satisfying un is a constant a times un minus 1 plus a constant b times un minus 2, where a and b are just fixed complex numbers. And the theorem says that if we have such a sequence, then there's an associated quadratic equation with roots lambda 1 and lambda 2 such that the following holds. If the roots are distinct, then un has this type of form. It's a linear combination of the geometric sequence with lambda 1 plus the geometric sequence with lambda 2, where C1 and C2 are constants that make the first two terms agree. If you have a multiple root, then instead of having two different geometric sequences, we have one, which is lambda to the n, and then we have a second sequence, which is n times lambda to the n. And those give us two independent solutions, and then every solution is a linear combination of those two. So the proof of part 1 is identical to what we did for the Fibonacci sequence. You first find two different geometric sequences satisfying the relationship. So with un being lambda to the n, we would get this equation right here, which leads to the quadratic equation, lambda squared minus a lambda minus b equals 0. And by the quadratic formula, we get these two solutions. And since the roots are distinct, we again can solve the linear system like we did before to get a unique solution for any choices of the first two terms. So that proof is identical. I'm not going to write down any more details there. So let's turn to the second part where you'd have a double root. Then we claim that the sequence n times lambda to the n is also going to satisfy this linear recurrence. So why is that? So if we have a double root, then in the quadratic equation, that means the discriminant is equal to 0. That's when you get a multiple root. And so a squared would equal negative 4b, which means that lambda is a over 2. So the lambda value, recall, is from the quadratic formula. So it's negative b plus or minus, the discriminant is 0. So that's where the lambda is coming from. Okay, so now let's insert the sequence into the recurrence and show that it works. And lambda n into the recurrence star. So on the left-hand side, the nth term would be n lambda to the n. We want to show this equals a times un minus 1 plus b times un minus 2. Okay, so we need to show this is true. And then just multiply it out and cancel lambda to the n minus 2 on both sides. Next, let's insert these expressions for lambda and a. So lambda is a over 2. So this becomes n a squared over 4. And these are equivalent statements here. And then this is a times n minus 1, a over 2. And b is a squared over negative 4. So minus a squared over 4 times n minus 2. Okay, so, and that should just be, multiply this out and see that this all works out. So what do we get on the right-hand side? I get a squared over 2n minus a squared over 2 minus a squared n over 4 plus a squared over 2. So these cancel out. And then this is just a squared n over 4, and we have agreement. QED. To complete the proof, we have to show that if un is any sequence satisfying the recurrence, then there is a linear combination. So then there exist constants C1 and C2 such that the Wn sequence agrees with the Un sequence. And to do that, it suffices for Wn again is C1 lambda to the n plus C2 n lambda to the n. All we need to do is get the first two terms to agree, so W0, which is C1 plus C2 times 0, so it's just C1, should agree with U0. Alright, so I can certainly solve that equation, we just let C1 equal U0. And then I need W1, which is C1 lambda plus C2 lambda, or in other words, C1 plus C2 lambda, to equal U1. And thus I can solve for C2 lambda doesn't equal 0 here, and we get C2 is uniquely determined like this, which completes the proof. Now let's do one example. Let's let UN be the sequence whose first two terms are 0 and 1. And instead of satisfying the Fibonacci recurrence, let's say the nth term is the difference of the preceding two terms. So 1 minus 0 is 1, 1 minus 1 is 0, 0 minus 1 is negative 1, and then we get another negative 1, and then we're back to 0. And you notice as soon as we get these first two numbers repeated right there, everything after that is going to be the same. So any two given numbers determine all of the terms following it, and so we get a periodic sequence with period 6. Now our theorem gives us an explicit formula, so let's see what the theorem actually gives us. So this time you let UN be lambda to the n, and we look at the associated quadratic. I always just go back to scratch when I do these. Okay, so that's the recurrence right there. And so you get lambda squared is lambda minus 1. Lambda squared minus lambda plus 1 is 0. So lambda is negative b plus or minus the square root of b squared minus 4ac all over 2a. So this time we're getting two roots, like this. And so let's let lambda 1 be 1 plus root 3I over 2, and lambda 2 be 1 minus root 3I over 2. Alright, so we've got distinct roots, lambda 1 and lambda 2. So UN must be of the form constant C1 times lambda 1 to the n power, plus another constant C2 times lambda 2 to the n power, and we just solve for C1 and C2. So I want C1 plus C2 to be the first term of the sequence, and C1 lambda plus C2 lambda 2 to be the second term, giving us, by solving the system of linear equations, C1 is 0, 1, 1 lambda 2 over lambda 2 minus lambda 1. So that's minus 1 over lambda 2 minus lambda 1. Lambda 2 minus lambda 1 is minus root 3I. Minus root 3 over 2 minus root 3 over 2 minus root 3I. Okay. 3I. So this is just 1 over root 3I. That. And C2 is 1 lambda 1, 0, 1 over minus root 3I, the same denominator. So 1 minus 0, like that. And therefore UN equals C1 times lambda 1. Lambda 1 again is 1 plus root 3I over 2 raised to the nth power plus C2 times this conjugate quantity. Quite a wild thing here. So that is the way to describe this very friendly looking sequences of zeros and ones. This periodic sequence of zeros and ones can be described explicitly by introducing the imaginary quantity square root of 3i and writing it like this. So that's valid for n greater than or equal to 1.